guys. So the other day we worked with Euler circuits, right? We worked with Euler circuits, we started talking about Euler paths, and then today we're going to exclusively talk with Euler paths, just because I want you guys to be able to see the difference between the two more so. Now again, the other day we just started getting comfortable with the idea. Today I want you to be able to go further with it. So be able to analyze both at the same time, right? So when we worked with Euler circuits the other day, again, Euler circuits, we knew that one, since it's a circuit, it has to end where it started, right? And a path, it ends at a different point than where it started. So the difference between a path and a circuit, again, a path ends at a different vertex than where it started. A circuit ends at the same vertex where it started. And since they're Euler paths and Euler circuits, you can only use each edge once. It can only be used once. So we looked at this before, right? Where we had this figure, right? And we knew that that was an Euler circuit, because again, you pick a starting point, and can I trace and use every single edge once, and then end up where I started? In this case, we could, just like I showed you. If you start here, right, every single edge gets used once, and I end up back where I started. That's why that's an Euler circuit, right? And then an Euler path, again, it was a figure where you finish at a different vertex where you started. But the difference now is that, again, it's making sure that you use each vertex once. So what we had the other day was something that looked like this, right? We had that. And we knew that, again, this was an Euler path because, again, you can start at a point right here, right? And then use every single edge once. But now the problem is we're ending at a different point. And then if you were to try to go back, that's a problem because, again, we already used it. You can't ever go back. You can't ever go back. So again, since we finished at a different point where we started from, that's why it's a path, right? When you go back to the point where you started from, that's an Euler circuit. And there were easier ways for us to just analyze Euler circuits, right? We ended up noticing if we analyze the degrees, it helps us with everything. So for example, if we look at this point, right? This has a degree of 2 because it goes 1, 2. That has a degree of 2, 1, 2. All of them have a degree of 2 because they all connect to 2 edges, right? So we said when it's all even degrees, that's an Euler circuit, right? An Euler circuit has all even degrees. It has no odd degrees. And again, even numbers, 2, 4, 6, 8, and so on. An Euler circuit has even degrees, has no odd degrees. No odd degrees. Now, if it had any odd degrees, it wasn't an Euler circuit, right? What an Euler path is, and it still uses that same concept just to be analyzing it. If we look at this Euler path, we know that this degree is 2, right? Because it connects 1, 2. We know that this one here is 2. 1, 2. We know that this one here is 1, 2, 3, 4. So far we're good, right? Because these are all even numbers. But now if we look at this, this is 1 because it just connects to 1. That's 1 because it connects to 1. So now automatically the difference here is they're not all even numbers in degrees. We do have some odd numbers. So when you have odd numbers, automatically it's not a circuit because a circuit can have no odd numbers. But what an Euler path is, whenever you analyze this, an Euler path can have 1 or 2 odd number degrees. It can have 1 or 2 odd number degrees. That's it. 1 or 2, no more. Because what happens, again, if it has more than 2, then it's none of this. Again, an Euler path can have 1 or 2. It can't have more than 2. And since over here it has just 2, that's why it's an Euler path. If it had, let's say, 4 or 5 of them, automatically that would be none of this. It'd be neither of these. Because again, the most important thing to analyze is that when it's an Euler path, it can have 1 or 2, that's it. The second it has more than 2 odd number degrees, it's nothing. It's neither of these. And again, that's where it becomes a lot easier to analyze just because there is this rule, right? And again, I do want to write that rule out just for you guys to be able to see it a lot easier. Because I do think that it does help just to be able to have it as a resource. And again, I do think that you guys now are more comfortable with seeing it, which does help a lot. So always remember, if you have an Euler circuit, we know it's no odd number degrees. It's no odd number degrees. It has to be all even, right? Has 0 odd number degrees. If it's an Euler path, we know automatically that it has 1 or 2 odd number degrees. And this does help. Again, it can only have 1 or 2, it can't have more. And if it's none of these, it's gonna have more than 2 odd number degrees. It's gonna have more than 2 odd number degrees. And this should help a lot, guys. Okay, just always think in the back of your mind, if it has none, it's an Euler circuit. If it has 1 or 2, it's an Euler path. If it has more than 2, it's nothing. It's neither of them. And now again, knowing this, now we can actually apply it just by looking at the graphs, because it becomes so much easier to actually have a rule like this where you can actually calculate the degrees of each vertex, which you guys can do perfectly, right? And it becomes a lot easier to do that than just trying to play around and trying to trace every single thing to figure out if it is an Euler circuit or an Euler path, right? So now looking at this, let's say I gave you this figure, right? We have this, right? We have that right there. We have this right here. We have that. Right? Let's say we have that figure, and I want to figure out if this is going to represent an Euler path, an Euler circuit, or neither, right? I want to figure out all of that. And again, instead of just playing and tracing, what we can do, just figure out what all the vertices are. Figure out what all the degrees are, because it does help drastically. So when we look at the first one, 1, 2. When we look at this one, 1, 2, 3, 4. When we look at this one, 1, 2, 3. Right? When we look at this one, 1, 2, 3. When we look at this one, 1, 2, 3, 4. So once we see that, again, we notice it has some odd number degrees, so it can't be an Euler circuit. And then we have to analyze it. It has 1, it has 2, and since it has 2, right, it's going to be an Euler path. Because again, the definition of an Euler path, it has 1 or 2, and since it has 2 odd number degrees, that's why it's an Euler path, right? Let's check this out now. Let's say I were to give you, this. Let's say we had that, right? And again, it does get to a point where you start to get comfortable seeing it, right? We have this, we want to figure out again, whether it's an Euler circuit, an Euler path, or neither. Now we're looking at that, right? We know that this one has 2. We know that this one has 2. We know that that has 1, 2, 3, 4. We know that this has 2. We know that that has 2. So if we look at all the numbers, 2, 2, 4, 2, 2, they're all even numbers, right? There's no odd numbers. So the fact that they're all even, there's no odd, automatically we know that's an Euler path. Because in Euler path, again, it's all even, there's no odd numbers, guys. I'm sorry, Euler path. I'm an idiot. It would be an Euler circuit, guys. Euler circuit. Because when it comes to an Euler circuit, and I apologize for that, when it comes to an Euler circuit, they're all even, guys. Every single one of these degrees is going to be even. There's no odd number degree. That's why it's an Euler circuit. And then just one more, guys, for you to be comfortable seeing this. let's say now that I were to give you this, right? Where we have a triangle, right? We have this here, we have that there, right? And again, these are all examples of vertex edge graphs, which you've been working with, and you actually did an excellent job with them all. Say we have this, right? And we're looking at that, we want to figure out if this is an Euler path, an Euler circuit, or neither, right? We know that this one here is 1, right? Because it connects there. We know that this one here is 1, 2, 3. That's 3. We know that this one here is 2, 2. We know that that's 1, 2, 3. And we know that that's 1. And now automatically, we start noticing something why it makes it different. 1, they're not all even, right? So if they're not all even, it's not an Euler circuit, right? For it to be an Euler path, it can have 1 or 2 odd number degrees, right? But when we look at the odd number degrees, it has 1, it has 2, has 3, has 4, right? Since it has 4 odd number degrees, since it has more than 1 or 2, automatically it becomes an neither. It's nothing. It's not an Euler path, it's not an Euler circuit, and the reason again it's neither is if it has more than 2 odd number degrees, it's neither, right? So always remember, if it has none, if it has all even numbers, it's an Euler circuit. If it has 1 or 2 odd number degrees, it's an Euler path. And if it has more than 2 odd number degrees, it's neither. Again, because if we were to pick any point, it would be impossible to ever use every single edge once without being able to repeat it. It'd be impossible to ever be able to trace all of this without being able to go backwards, right? See, anything you try to do to actually use all of them, you always have to go backwards and use each edge. That's why it's neither. Again, guys, any questions, feel free to let me know, okay? Take care.